Hi, this is Baird Givens, and in this video, we're going to introduce the idea of images and pre-images of sets and do a couple of examples. Now, this concept of images and pre-images of sets may be review for many of you, but not necessarily for all of you. A lot of you might have seen it kind of briefly in other classes, but not really mastered it. So I'm going to go ahead and just start from the beginning with the definition. I'm not going to assume that you already know what it is. So let's start by going over the definition. All right. This comes up when we're talking about a function that goes from one space to another space. So let's say I have a function f that goes from some domain x to some codomain y. And then we'll think of A as being a subset of the domain and B as a subset of the codomain. Then the image of A under F, it's written f of A. I might sometimes also say the forward image, or I might just say f of A. But at any rate, it is defined as a set. It's the set of all elements of the form f of x, where x is in A. So it's all the things that can be output if you start with something in A, all of the possible outputs starting with inputs from A. Now the pre-image of B under F, it's written as F inverse of B. You might hear me sometimes say F inverse of B, or the inverse image of B, or the backwards image of B, or the pre-image of B. These are all things that I might say when I'm talking about the pre-image of B. It is the set of all things of the form X such that f of x lands in B. So it's saying all the things in your domain that the function makes them land in B. Okay? Just to make sure we're on, all oriented the right way. A starts out being a subset of your domain, and then f of A is all of the outputs that you get. If you start with points in A, what are the possible outputs that you get? So f of A is in your codomain. B starts out in your codomain, and then the pre-image of B is all of the things that if you were to start with them, they would end up landing in B. So the pre-image of a set in your codomain, the pre-image is a subset of your domain. All right, let's do some examples to help make this more concrete. So let's start with an example of f of x being sine of x, f of x being sine of x. So if f of x is sine of x, and I want to know what is the forward image of 0 to pi over 2. Using the definition, it's the set of all f of x. I'm using this definition right here, the set of all f of x, which is sine of x, such that x is in this set, 0 to pi over 2. And that means that x is in the first quadrant. And so if you think about the values of sine of x in the first quadrant, the values that sine of x can take on are 0 to 1. Okay, next, and I just noticed that I have a mistake here, so I'm going to erase this and back it up. Okay, and we'll fix that. F inverse of 1, using the definition of preimage, that's the set of all x such that f of x is an element of singleton 1. F of x is an element of singleton 1. Well, being an element of singleton 1 means that sine of x has to equal 1. That's the only way to be an element of singleton 1 is to equal 1. And using our knowledge of trigonometry, that is, well, x could be pi over 2, but it could also be any multiple of 2 pi plus pi over 2. So this would look like pi over 2 plus 2 pi k, where k is an integer. So it's interesting to notice that the set I started with here just had one element, but its pre-image has infinitely many elements. And that can happen, particularly when f is not an invertible function. Sine of x is not invertible unless you restrict its domain. And so because sine of x is not invertible, the inverse image of a set might have like a different number of elements. It could have more elements. It could actually have fewer elements. You don't necessarily know. Now, we also might have wanted to think about this using a graph of sine of x. So when you graph a function, we're always thinking of the horizontal axis as the domain and the vertical axis as the codomain. And I know the graph of sine of x, sort of like that, okay? And when I talk about the forward image, so when I talk about the forward image of the closed interval 0 to pi over 2, when I talk about that forward image, I'm talking about this little stretch here in the domain from 0 to pi over 2. From 0 to pi over 2. And I want to think about, well, which part of the graph does that correspond to? That corresponds to this part of the graph. And then which part of the codomain does that correspond to? So if I go up to the graph and then over to the vertical axis, I get this part of the graph. So I go up this way and then over that way. So when I take the image of a function that's graphed on the xy plane, taking the image basically means taking the set on the horizontal axis, going up to the graph, and then going over to the vertical axis. And then the vertical axis is what we output. And so we can see here, this 0, 1/2 is the A that we're looking at, and then f of A is 0 to 1. Similarly, if I were to look at f inverse of 1, that means I take the point 1 right here on the in the codomain, which is the vertical axis, and then I think about going across from that point to the graph, and then anywhere I touch the graph going down. Oh, my picture is terrible. Okay, so this goes down right here. This goes down right here. It goes down to the pi over 2's, 5 pi over 2, and so on and so forth. And so because the function is not 1 to 1, there's infinitely many places. All right, so that is that first example. Let's do the second example. For the second example, I just have a function that goes from the set 1, 2, 3 to the set ABC. And f of 2 comma 3, f of 2 comma 3, this is the set of all f of x such that x is in 2 comma 3. The set of all f of x such that x is in 2 comma 3. So that would be f of 2 and f of 3. F of 2 is b and f of 3 is a. And so this is AB. Let's move this one down a little bit. Next, f inverse of AC. Using the definition of preimage, this is the set of all x such that f of x is an element of a comma c. That is the definition. So that is the set of all x such that f of x equals a or f of x equals c. So it's all the inputs whose outputs are either a or c. So which inputs give me a as an output? 1 and 3. Now, which inputs give me c as an output? There aren't any, right? There aren't any, so that's where I stop. All right, so f of 2 comma 3 is a comma b. F inverse of a comma c is 1 comma 3. And this example shows that it can happen that you have an element in your set B, in this case we had this element C, that doesn't, like nobody hits it, okay? So when I'm doing F inverse of A comma C, the C is almost like irrelevant. It doesn't matter because nothing goes to it. So it doesn't make anything happen over here. If I had just looked for F inverse of singleton A, that would have been the same answer. And that can absolutely happen. It can absolutely happen. It could be that some things in B over here just never get hit, but we still can compute the pre-image this way. All right, last example. Let's say we have a function f that goes from R2 to R, R2 to R. And the function that we're going to look at is going to be the function f of xy equals x plus y. So let's write down what each of these things are using the definition of image and pre-image. So f of the unit square, f of 0, 1 cross 0, 1. That is the set of all f of x. So that's the set of all x plus y. I'm using, again, this definition right here of f, the forward image. So x plus y such that x is in 0, 1, and y is also in 0, 1. Really, it's that x comma y is in 0, 1 cross 0, 1, but I just rewrote that a little bit more cleanly. So it's the set of all sums that you can get where you add two numbers that are both between 0 and 1, and they include 0 and 1, including both endpoints. And if you think about that a little bit, I think you can convince yourself that you can get all possible numbers between 0 and 2, including 0 and 2. Okay, the smallest you can get is 0 if x and y are both 0. If x and y are both 1, then you get 2 as your answer. And if you think about as x and y increase from 0 to 1 each, you would get all possible numbers between 0 and 2. Okay, now let's look at the inverse image of the open interval from 2 to 3. So let's use the definition of pre-image from right here to write down what that would be. This is the set of all x comma y such that f of x comma y is an element of the open interval -2 to 3. I can rewrite that as the set of all x comma y such that -2 is less than f of xy, which is x plus y, which is less than 3. And honestly, I could just stop right there. I think that's my answer. That is my answer. Uh, but let's also just graph it just to make sure that we kind of understand what's going on. So that is my pre-image. That is my forward image. Let's go ahead and graph what that pre-image looks like. So that's a set of ordered pairs. So that's going to be a subset of the domain, which is the plane. So that is a subset of the domain. And it's a set of all ordered pairs such that x plus y is between -2 and +3. Well, x plus y equals -2 is a line that goes through -2 on both the x and y axes. And x plus y equals 3 is a line that goes through 3 on both the x and y axes. And x plus y is greater than -2, so it's above that bottom line, and it's less than -3, so it's below that top line. And so I claim that it's this shaded region right here, that shaded region right there. Okay, so that was a quick blitz through the definition of forward image and pre-image, or image and pre-image of sets under a function. And we're going to be doing a lot of this as we learn about the meaning of continuity in topological spaces. So you'll get plenty of practice. All right, thanks for listening.